Hi, my name is Justin Cam, and today I'm going to be talking about forward kinematics, which is my favorite topic in ECE 470 this semester. Forward kinematics is an extremely important topic because it allows us to identify the position and the orientation of the robot's end effector given the joint angles of the robot. I was able to gain exposure to forward kinematics through the course lectures, as well as the example problems we got in the homeworks and in the exams. And then also there was a dedicated forward kinematics lab in the course lab. In this lab, we were able to calculate the end effector position of the UR3 robot, and we were able to gain this information and combine it with the information we got in the inverse kinematics lab to use in the final project, where we were able to move the robot's arm around to different locations so that we could pick up and place blocks for our final project. Basically, when solving a forward kinematics problem, you need to examine the diagram provided to identify the different vectors. For example, the omega vector, the v vector, and the q vector. And then we combine these all into creating the screw vector, which we can then convert into a screw matrix to plug into the final transformation matrix equation. I'm now going to walk through an example problem to solve a forward kinematics problem. Okay, so this is the problem we're going to solve today. Here we can see that there are 4 joint angles we need to solve. This is the initial S frame, and this is the body frame. So to start off, we're going to solve for the omega vectors, which is a 3x1 vector. So omega 1 is going to be the direction in which the rotation axis is. So we can see it's going in this direction, which correlates with the z direction in the space frame. Therefore, omega 1 is equal to 0, 0, 1. Omega 2 and omega 3 can be found in a similar way. You can see both of these rotation axes are also aligned with the z, which means that these will also be the same. Finally, to solve for omega 4, we see that this last joint is not a revolute joint, it is a prismatic joint. And therefore, omega is 0, 0, 0, because that's what the omega is for prismatic joints. Now we're going to solve for the q vectors, which are the positions of the rotation axes with regards to the space frame. So q1 is aligned with the initial space frame. So it's going to be 0, 0, 0. q2 we see is offset by distance L1 in the y0 direction. So we can say that q2 is equal to 0, L1, 0. For q3, we can see that it's now offset by a offset of L1 plus L2 in the y direction again. So it's going to be 0, L1 plus L2, 0. And then finally, the q4 does not matter because it is a prismatic joint. And then finally, we're going to calculate the v, which is equal to negative omega cross q. So the v1 is equal to omega 1 cross q1, which is going to be 0, 0, 0. v2 is equal to omega 2 cross q2. So we have for the first, it's a2 b3, which is 0 times 0, which is 0 minus 1 times L1. So that's going to be negative L1. But it's going to be negated, so it's just going to be positive L1. And then for the others, it's going to be 0 and 0. And then for V3, A2 is 0, B3 is 0. So 0 minus 1 times this term in the middle. So it's going to be 0 minus L1 plus L2. And then A3 is 1, B1 is 0, A1 is 0, and then B3 is, so that's the middle, second term is going to be 0. And then that last term, A1 times B2, which is 0 times this term. So it's 0. And then A2 times B1, which is also going to be 0. So then this is V3, but this is just omega cross Q. We need negative omega cross Q. So this is going to be positive again. So then this will be L1 plus L2, 0, 0. And then finally for V4, for a prismatic joint, the velocity is just in the direction of the motion. So we can see that theta 4 is going in the positive z direction. So V4 is going to be equal to 0, 0, 1. Now we need to create the screw vectors. S is equal to a 3x3 matrix omega times a 3x1 vector here, and then followed by bottom row of all zeros. Now this omega matrix is given by this equation. So let's first start by finding S, S1. Omega 1 is 0, 0, 1. And so the only value that is not 0 is omega 3. So we have 0, negative 1, 0, 1, 0, 0, 0, 0, 0. And then this column right here will be the V values, which are all 0. And then the bottom row is all 0 as well. Now S2. We'll do the same thing. The omega matrix is going to be the same again because the omegas are all the same. So it's 0, negative 1, 0, 0. Oh, not 0. 1, 0, 0, 0, 0, 0. Now instead, V2 is going to be L1, 0, 0, 0, 0, 0, 0. And then S3, the same omega, 3x3 matrix. And now for V3, it's going to be L1 plus L2, 0, 0, 0, 0, 0, 0. And then finally for S4, the omega matrix is going to be all zeros now because omega 4 is all zeros. But then for V4, it's going to be 0, 0, 1 because that's what V4 is. And then 0, 0, 0, 0. Okay, finally, the last thing we have to do is calculate the M matrix, which is the position of the end effector. So basically, to find the M matrix, we can see that the body frame, X, Y, and Z axes are all perfectly aligned with the initial space frame axes. So the 3x3 matrix in the M matrix will just be 1, 0, 0, 0, 1, 0, 0, 0, 1. This is because it's perfectly aligned, the body frame and the space frame. It doesn't change at all. And then for M, the vector, the 3x1 vector here is going to be the position of the end effector. So we can see that it is offset by L1 plus L2 in the Y0 direction. There's no change in the X direction. So it's going to be 0 here, L1 plus L2 here. And then finally in the Z direction, it's offset by L0. So L0 there. And then 0, 0, 0. And for the M matrix, this last value in the bottom 4x4 is 1. So now finally, we have all the screw matrices as well as the M matrix. So then we can put this together in our final formula. T is equal to E S1 theta 1 T. I'll just move this to the next page. T S 2 theta 2 E S3 theta 3 E S4 theta 4 and then times M. So this value will give us the final end effector position. There are also other ways to do forward kinematics, like with the body frame, but for this example, I just did it with regards to the space frame. But if we wanted to do the body frame, you would move the M to the front, and then to calculate the inside part, you would have to find the omega and the Q and the V with respect to the body frame coordinates. So yeah, that was how to solve a forward kinematics problem. I'm going to stop sharing my screen here now. Okay, and then finally, we're going to be, I'll share my screen now on my laptop. This is another resource that we can use to learn more about forward kinematics. So this is a textbook from Clemson University. There's actually a lot of different ways to solve forward kinematics. There's the trigonometry method, the Denevitt-Hardenberg convention, and the screw theory. We learned about these other methods in class, but for this example, we use the screw theory method. So we can see that that's going to be in section 2.6. So here's the section that discusses the method that we just used, the POE, product exponentials. So we have to calculate the twist of the robot, screw, and then we plug it in to one of these two equations. This top one is the one I just used for the space frame, and then this bottom one, if you wanted to do the body frame method. So section 2.6 in this textbook will give more information about the product of exponentials method that I just used. But in case you wanted to learn more about the other methods, like the trigonometry method or the Denevitt-Hardenberg method, this article also has a lot of important information about that as well. Okay, thank you so much. I hope you enjoyed this video.